Recording is in progress. Welcome to our class today, Wednesday, March 2nd, 2022. I hope that you have enjoyable break and you study well for your exams. And you will continue till where we stop. Yesterday, I sent exam instructions. We'll discuss it in a bit. Then we will start with our class. Let me open the announcement. Can you share the? Can you see the owl screen, guys? Okay, thank you, guys. Thank you, everybody. So the message said, dear all, please note the following. The midterm course will be this Friday at 9 a.m. The exam venues will be UCC 41 and UCC 146. Whose last name started with A to F will be in UCC 41 because it's a bit small room. And the remaining student will be in UCC 146, whose their last name started in letter G to Z. The exam is a closed book, just your pen, pencil, eraser, whatever you need. But no book, no phone, no laptop is allowed. The exam will be mixed format. You will have 8 multiple choices, 8 true and false, and some other question. It's a quick answer. There's no a lot of writing. So the exam is so easy, but you need to study well. And those I receive, guys, a lot of emails from students asking questions. I say it many times in the classes, but I'm sure they do not attend the class. They don't read the course outline as well. And they don't see the videos also on the YouTube channel. I don't know what they are doing. I don't know what they are doing. I'm not talking about you guys. You are always attending and know what's going on. But some of students, they sent, even in assignment 1, I'm surprised. This is the first year this is happening. Till the moment 9 students, they did not submit, and they start using the self-reporting absence. It's one of your right. The university gave you this right to invest it or to use it when needed, but not in an assignment that is now more than it's almost a month assignment 1 now. And it was supposed to be submitted earlier, before the reading week. It was due before the reading week, but I give you an extension another 9 days, and they are using self-reporting absent. Okay, you use it in the deadline, the next day you have to submit it. So those who use SRA for the deadline, the next day you have to submit it. 24 hours after the SRA, you have to submit it. So today is the last day for them to submit. I don't know what's wrong with them. The assignment, if you sit in for the assignment 2 hours, you will solve it all. It's not a difficult assignment. It's almost the same as example that you are taking in the class. Since we post the assignment, we covered the material that will solve more than 60–70% on it. The same week, you are done with whole material to do your assignment. If you start in each week, you solve 2 questions, done. Then you can submit before the reading break. I'm talking for those who are late. Those who submitted, well done, guys. Okay. Please be 15 minutes before the starting time. So try to be there at 8:45 to be seated by the proctors. As we mentioned many times, but I still receiving emails. What is the material? Even after the announcement. I don't know if you don't read the announcement and they send me, hey, hello, professor. Can we know what is the material cover? We mentioned that many times before and in the announcement. So I don't know, guys. So it's handout 1, 2, 3, 4, pumping lemma study guide for handout 4, 5 and 5A, tutorial 1. It has many examples. Class note 1, 2, 3, 4, 5, 6, 7. Lecture recordings, if you don't remember or if you don't attend the classes. Recommended books for the course in the course outlines, but if you attend the classes, understand the handout, the class notes, that's done. But if you want to see more examples, it would be good if you look at the example in the textbook. And any other resource you feel you are comfortable with. The internet and the web has a lot of resources about theory, computation theory. Please study well, sleep well, and be safe, because the exam is in the first thing in the morning, so sleep well. This would help you to concentrate and answer very well. Wish you all the best of luck, guys. I hope that everybody in this class will do or perform well. So if you have any question about the exam, please go ahead now and mute your mic and ask. Questions? Okay. So I hope this is clear. So we'll start with handout 7 today. Can you see handout 7, Turing machine? Okay, thank you all. Okay. So today we will start with Turing machines. Till today, we covered deterministic and non-deterministic finite automata and regular expressions. Then we move one level more to context-free languages and context-free grammars. And we saw the parse tree, the pumping lemma for context-free languages, which is in handout 6. And today we move one level more for Turing machine. So what is Turing machine? We have finally arrived at a complete model of computation, Turing machine. Turing machine captures a model of computation that has full effective range of computational power. If you can compute it, there exists a Turing machine that can compute it. Fundamental limitation, even a Turing machine cannot solve some problem. There are still some problem that is incomputable till today. And we will see the $1 million question. We'll talk about it. Turing machine component. The Turing machine consists of the following component: tape, an infinite tape of memory cell, head that read and write head pointing at single memory cell on the tape. The head can move left and right. If you remember in the context-free grammar, we are using a stack. We can move one step forward. So here we can read left and right. Control, what is the control? It's a finite automaton that control movement of the head reading from and writing to the tape, it has explicit accept and reject states, and the Turing machine stop, or we call it halts, whenever it reaches one. When we reach to an accept state, it's halt or reject at the same time. Technically, the tape is not infinite in both directions. It has a beginning, but continues forever. Initially, the input string appears on the tape starting at the beginning. All cells beyond the input are marked with empty. This is the symbol of space, this one. So when we use this symbol, that means that this cell is empty. A Turing machine is essentially a finite automaton with the ability to read and write from a memory tape. As simple as that. It is a finite automata or automaton with the ability to read and write from a memory tape. So this is the Turing machine. I have A, B, B, then these, that means they are empty cells in the memory. So the head here at A, if I ask it to move right, it will read another A and the pointer will point to this cell. Then I ask it to go back to left, then it will read another A. As the Turing machine read a character from the tape, it may move the heads left or right and may write a new character to the tape. We might replace this one with a new character. We will see in examples. These examples. A Turing machine erasing the last symbol in the input tape. So the Turing machine is at A. So the cell is not blank. Move right. We'll move to B. Then we will ask it to move left again, right again. It will point to empty cell. And we ask to move the last symbol. Since I reached to empty, then I'll back to this one and replace it with a space. Here are the steps to erase the last symbol in the input tape. I think it's clear. The definition of Turing machine. So in order to be consistent with the definition of non-deterministic finite automata, push-down automata, and to make your life a little easier, we'll follow along the lines of Peter Lenz's definition of Turing machine instead of Spicer's. See comparison here. If you click here, you'll see the comparison between Spicer's, which is the author of one of our recommended textbook, but in our course, we use Peter Lenz's definition. The tape may extend infinitely in either direction, and the read head is free to move beyond the input in either direction. Instead of having a single final accept state, you may allow F to be linked to set of Qs, which is a states, to be a set of accept states. We might have more than one accept states. Instead of having a single explicit reject state, you can assume, like in an FA and PDAs, that the input is rejected if there is no transition out of the current state. You may leave it to faith or to interpret Google search that two definitions are essentially equivalent. If you look for the comparison, you will end and understand both definitions. You will end at that they are equivalent, but we use this definition, Peter Lenz's definition. This is the definition. A Turing machine is a sixth tuple. The first element of that tuple, which is the set of state, finite set of state, sigma, which is the input alphabet, not containing the black symbol. The black symbol should not be, will not be contained in the input alphabet. Then tuple alphabet where empty belong to the tuple alphabet and sigma also belong to that alphabet. Delta Q times gamma will give us the set of Q's times gamma, L and right transition function. This is left and right transition function. Move left, move right. Q naught is the start state and F is the set of final accept states. We said we might have multiple reject state and multiple accept state. You remember the string copy language example that we talked about it in the last handout. Recall the string copy language L, WW, where W belongs to the alphabet of 0, 1, star. So we use pumping lemma for context-free languages that L is not context-free, meaning there is no CFG that can generate this language, or similarly to the push-down automata that can recognize it. Let's now see how Turing machine is able to recognize this language. As a simplifying assumption, let's assume there is a delimiter hash between the two substring, W hash W, where W belongs to 0, 1, star. Move back and forth across the tape to matching position on either side of the delimiter. If the symbol don't match or no delimiter is found, reject and halt. This is the delimiter. This is a symbol will show me that the first string is done. And here is the second string beginning. Okay. So when all the symbol on the right of the delimiter hash have been crossed out, check if there are any uncrossed symbol left on the right. If so, reject. Otherwise, accept. We will see now. Here. The notation A prime is used to denote the current location of the head. Let's we have the string 011000. This is the first string. So this one we use it to see, because in the example we said that we have WW. How to know that the first W is done or the second W? We add the hash to separate the language. We cannot use the space because it's not part of this alphabet. It is part of the Turing machine alphabet, as we see here in the definition. In the alphabet, this one is not used, so we add the hash. So we read 0, here begin, and we start crossing out the one with X. So we start X, 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 we read the hash, then we back X, X, X till we have the last one. Then we would accept that it's two similar string that belong to 0 and 1 alphabet. Questions? Okay, guys, we start one by one and we do the X's till we done all the steps. Here you see, till we reach to this situation, then we will accept the alpha or accept the language. Let's draw the state transition diagram for L. So in a class C 3.9 example in your course text to see the state transition, if you want. We will have in the class notes some similar examples also. We saw the strategy of recognizing L, W hash W, where W to belong to 0 and 1. What about arbitrary copies? W, 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 etc. Recall that we proved this counting language not a context free. We said that a to the power I, b to the power I, c to the power I, where I is greater than 0, it's not a context free language using pumping lemma. But with Turing machine, we can follow the strategy of moving back and forth, crossing out symbols at corresponding position. And like the string copy language, this one, we can design a program to count arbitrary non-infinite copies. Because we said that with push down automata, we can compare two things. So we can know that the number of A's equal number of B's, but we cannot know that the number of C's equal the number of A's and B's. Do you remember this example in pumping lemma with push down automata before the reading week? So Turing machine is able to compare A's, B's, and C's, same as W's. We compare two W's, and we said that we can do whatever we want, number of W's to compare them. They are equal string. So it would be easy to equal that the number of symbols are equal. So a Turing machine can solve a to the power I, b to the power I, c to the power I, where I is greater than 0. So we'll talk this example. Let's see a Turing machine performing multiplication. Remember, in our model of formal language, we are not computing the answer k to the input I times j. Rather than we are inputting I, j, k and recognizing the language where I times j equal k. For simplicity, we are using unary representation. Let argument 1 be I, repetition of a, argument 2 to be j repetition of b, and argument 3 be k repetition of c. The language then become a to the power I, b to the power j, c to the power k. I, j equal k, and I, j, k is greater than 1. To go more in details on this example, you can see 3.11 in your textbook. Okay. So you remember this one, they have the same repetition, one argument I. What about if I have the number of A's is not equal the number of B's or the number of C's? Or the number of A's and B's equal the number of C's? Turing machine can solve this example and can accept this language. But context-free grammar or push-down automata, regular language, they cannot accept it. Okay, guys. Let's see class note 10. Can you see, guys? Yes, no?
Yes.
Okay, sounds good. So this is a game like a hand or a class handout or a class note about Turing machine. Finite automata control plus no memory. Then it will be deterministic finite automata and non-deterministic finite automata. Push down automata, which is finite control plus memory stack, only stack. Then it will be a push down automata, PDA. How we extend that? By Turing machine. So what is Turing machine in simple term? It's a finite control plus memory tape that I can move one step left or right and can replace the symbol in that memory cell. A Turing machine has a finite control with tape. The tape is semi-unbounded, and any cell of the tape can be accessed by using the tape head. Here is the tape head. I can move left or right. Why we said semi-bounded? Because it has a start, but it doesn't have an end. A Turing machine has a designated accept and reject states. Remember states. Transition with delta. If I'm at state P and the tape symbol is X, then go to state Q with tape symbol Y and L, which means move left or right. We can replace it with R. By definition, I'm at state P and I have an X. Before the transition, after the transition, I'm at state Q with the head pointing to Y. After the transition, I'm pointing here now. So, and here the U, the V, they are still the same, but I replaced X with Y. This is the same as in the handout. Input alphabet is a subset of the tape alphabet gamma. What is the difference? That alphabet doesn't contain the blank symbol. Initially, tape contains the input W and the remaining cells are filled up with the symbol empty. If the input head tries to move to the left of the leftmost cell of the tape, then it will stay at its current position. It will stay at its current position. Definition: a Turing machine, it's a 6 tuples. We discussed that. Q0 is the start state, QA accept state, QR is a reject state. So I will use the QA to accept and the QR to reject. So the configuration of Turing machine, how it's go? With respect to an input W is a snapshot of the machine consisting of the current state, the current content of the tape, the position of the tape head. We represent the configuration as UQV, where Q belongs to Q, U is a string, UV is a string, and they are belongs to gamma star. Q is the current state, UV is the current control of the tape head position to the first symbol. So here Q is pointing to the first symbol. Here is U, which is a string, and V is another string at the left and right of the current position. So this is what they call it, the UQV configuration. And this is something like similar to Sipser's definition. At the end, they are the same. At the end, they are the same. A configuration C1 yield a configuration C2 in one step if the Turing machine can go from C1 to C2 in one step. Standard configuration that QA, Q accept are not equal to Q reject. And here M reject W. So if M accept W, if there exists a sequence of configuration C0, C1, C2, CK, that C0 is the start configuration, CK is the accept, CI yields that belong to the K. So M reject W, something like if CK reject the configuration. So these are not, just differentiation between two-way, the handout and the book. M halts on W if either M accept or reject W. So some student last year, I surprised that they think the halt, it's just only accept. No, guys. Halt means that M accept or reject W. If it's accept or reject, we said that the Turing machine halts. Done. Stop. We have a decision. So don't think it just accept. If for all W belong to alphabet star, M halts on W, which means accept or reject, whatever. So the language L of the Turing machine M, L of the Turing machine M, W belong to alphabet star, M accepts W. A language L is a Turing recognizable, we are saying. That the language L is Turing recognizable if there exists a Turing machine M such that L equal L of M. A language L is a Turing decidable or just decidable. We can say decidable or recognizable if there exists a halting Turing machine M such that L equal alpha. So we have two things, that if the Turing machine accept or reject, then there is a decision. If you remember, just before here, we said there is a decision, accept or reject. The halt means accept or reject, that we have a decision. Then we said it's Turing decidable. If the language L is a Turing recognizable, that means the Turing machine recognize that language, we say it's Turing recognizable and Turing decidable. We'll talk further about those maybe tomorrow or next week. I'm not sure. It depends on our progress. So example, the example that we have in the handout, if L is a to the power n, b to the power n, c to the power n, where n is greater than 0, it's non-context free language. How we accept this language in Turing machine? Check whether the input is of the form A star, B star, C star. If not, then reject. If yes, then accept. Across the first and across A, the first and across B, and then the first and across C. Continue. If there are still no C's, A's, and B's, then accept. If there are still that mean they are not equal, then reject. So if we have the string A, B, B, C, C, then we will ask it to cross the first A, then cross the first B, then cross the first C. Then you see here, I put it in sequence. Then cross the second A, the second B, the second C. Are there more symbols? No. Then accept. If there are more symbols, then reject. Okay, tell me. The Turing decidable, we'll start with decidable because it would be easier. If we reach to a situation like in this example, that the number of A's equal the number of B's and the number of C's, which is required by the description of the language, then we have the decision to accept that language as Turing machine. Then we call it Turing decidable or decidable language. And if the Turing machine can recognize that language, we call it Turing recognizable. Later, we'll say that is each Turing recognizable or Turing decidable, or each Turing decidable is Turing recognizable. We will have a comparison later. If the Turing machine can recognize the language under consideration, then we call it Turing recognizable. This is at this stage. We'll have more details later. If the Turing machine can decide, which is accept or reject, or what we say, call it halt. If the Turing machine can halt on that language, then we'll call it Turing decidable. What is the relationship between decidable and recognizable? We'll take it later. Clear? Great. Questions till here, guys? Questions till here? Okay, Brandon. A language L is a Turing recognizable if there exists a Turing machine that can recognize that language. But we didn't say accept or reject. And a language L is decidable if there is a Turing machine can halt on that language, which means accept or reject. What is the relationship between recognizable and decidable? We'll talk about it later. Maybe today, tomorrow, or next week, depends on the handout. But we'll cover this topic. Yeah, I told you there is a relationship between recognizable and decidable. But we'll talk about it later. Maybe in the next handout, I'm not sure. Maybe handout 8, 9, I don't remember. But we'll cover this topic. What is the relationship between decidable and recognizable? But till the moment, if the Turing machine can recognize the language, we'll say Turing recognizable. If there is a decision like this example, a to the power n, b to the power n, c to the power n, so we can accept or reject any string, then we call it decidable. And it will be recognizable for sure. Since it's decided, it is recognized. But how's the relationship? We have a separate topic to talk about it. Clear, guys? Any other question? Any other question? Okay. Sounds great. Okay. Can you see handout 8? Okay, good. So we'll start talking here about decidable and recognizable, and it will continue with the coming few handouts. So in handout 8, we'll talk about decidability and Church-Turing thesis. To solve decision problems, Turing offered an intuitive notion of what's called effective method for computing. What is the effective method for computing? We'll take a finite number of steps, always produce a correct result. Could in principle be done by a human with enough time, pencil and paper. Only need to follow instruction and no like creativity or extra step are required. It's a matter of time. So any computable, this is what will lead us to what? Any computable problem could be solved by pen and paper or pencil and paper. But it's the matter of time. The computer can solve it faster. This is in short term. What is the algorithm? An effective method is an intuitive definition of an algorithm. Additionally, a function is effectively calculable if there is an effective method algorithm to do it. So any problem I have, if I can convert it to algorithm, what is the algorithm? It's a set of steps. It's a set of steps that the computer has to perform, or the computing machine has to perform to arrive at the solution. A function is computable function if there exists a Turing machine can compute. So what is a computable problem? It should be calculable if there is an effective algorithm to do. The function is computable function if there exists a Turing machine that can compute it. So what is the Church-Turing thesis? It is every effectively calculable function is a computable function. If there is an algorithm here, if there is an algorithm that can calculate this function correctly, an effective method, then we say it is effectively calculable. If the function is effectively calculable, then there is a Turing machine can compute it, so it's a computable function. This is the theory. Every effectively calculable function is a computable function. In other words, a problem can be solved by an algorithm if and only if it can be solved by a Turing machine. If the problem could be solved by Turing machine, then there's an algorithm can do it. And if the problem can be solved by a Turing machine, then it should have a calculable function that can calculate it. Because, you know, if and only if, it's going both directions. Okay? Summary. In summary of the Church-Turing thesis is basically saying that Turing machine or equivalently Church lambda calculus can implement any algorithm. This, however, it's a thesis, not a theorem. Do you know what's the difference of thesis and theorem? So what is the difference between thesis and theorem? Anybody can tell me? A thesis is not always correct. Theorem is always true and proved. Yes. So the thesis, sometimes we have the null hypothesis. We assume something, and we could prove that it's not correct. So, guys, thank you. Cameron, Linjui, who else? Colin. Thank you for your answer. So the thesis is not proven. It could be true or not, but the theorem, it's proved to be true. It can be disapproved by a counterexample. Argument for include a huge set of non-Turing computable function, no known counterexample. Equivalence with other models like lambda calculus, cellular automata. So when we say a Turing machine can compute a function, what do we mean exactly? What do we mean? I'm looking for an answer tomorrow. Okay? I volunteer to answer the question tomorrow. I answered it when I was explaining before, but we need somebody also as a kind of revision tomorrow to answer this question in slide 6, handout 8. So we'll back to your question. What is decidable? What is recognizable? What is the relationship between both? Okay. So when a Turing machine is running and it has a particular string, so we might have one of 3 final states: accept and halt, reject and halt, loop forever, never halts. And when you write any program nowadays, you either get a result and stop, error happen and stop, loop forever, infinite loop. Telling the difference between a machine that halts but is just taking a long time from the one that never halts. We have to differentiate between both. That between an algorithm that taking long time to arrive at the solution, rather than one that enter in an infinite loop and never stops. We have to differentiate between both. That's why we define 2 classes of language. One for which the Turing machine always halts, always accept or reject, and one that may loop on certain inputs. Guys, is it clear now, decidable and recognizable? The answer in this sentence. Always the one that we have decision, and the one that will recognize the input, but it never stops. Go on an infinite loop. So, recognizing versus deciding. Let L be a language and M be a Turing machine. What is recognizable language formally? We say M recognizing L if M halts and accept all string. Note, we don't place any condition in what Turing machine should do if it's encounter a string S belongs to L. Accepts all strings that S belongs to L. We don't place any condition of what Turing machine should do if it's encounter a string S that not belong to L. Decidable language, we say M decides L if and only if M halts and accept all string. Here there is a typo, if M. Accept all string belong to L and halts and rejects all string that not belong to L. So recognizable, that we accept the string, whatever, we didn't say anything if it's decide or not, or keep an infinite loop. Decidable, we should have an accept or reject state. So thus, a Turing machine that decide a language always halts, whereas Turing machine that recognize a language must only halt for a string in the language. Thus, it follows that all decidable language are recognizable, but not all recognizable are decidable. Is it clear now? Brandon, is it clear? What is the difference? Okay, tell me, is it clear now what's the difference between recognizable and decidable? Okay, sounds great. So, Turing recognizable definition. A language is called Turing recognizable if some Turing machine recognizes it. The class Turing recognizable is sometimes called the recursively enumerable languages. So it's the same. Turing recognizable or recursively enumerable, they are the same. Turing decidable, a Turing machine that always halts given in any input is called a decider because it's always halt. We say it decides whether a string is in the language or not. A language is called Turing decidable or decidable if some Turing machine decided. The class of Turing decidable is sometimes called recursive languages. So if it's Turing decidable, we call it recursive language. If it's Turing recognizable, it is recursively enumerable languages. This is the language hierarchy. All languages, recursively enumerable, Turing recognizable, recursive, Turing decidable, context-free grammar and push-down automata, DFA, NFA, and regular expression. Clear or not? Questions? Questions still here, guys?
Sorry, Professor, do you mind if I ask a quick question?
Yes, sure, go ahead.
Thank you so much. So just back to the recognizing versus deciding. So whether it's recognizable or decidable language depends on the Turing machine that you're putting it into? Because it sounds like if you put one string in, it can halt and accept all strings in both cases. But the only sort of impact is if you put one in that isn't part of that language. That's the difference. So am I able to put the same string and language on two different Turing machines, and that's the output?
No, what's the thing is that Turing decidable is a subset. Here you have to understand the relationship first. Turing decidable languages is a subset of Turing recognizable. What is the difference? The Turing decidable will give you a decision, accept or reject. It's halt. Anyhow, if the string is part of that language, it will halt, it will reject. If the string is part of that language, it will accept. Turing recognizable has a third case, which is accept or reject, because we said Turing decidable is a subset of Turing recognizable. If a language that would accept or reject, or sometimes for certain input that not belong to L, but the program will still run or accept it to compute or recognize it and start running and go in infinite loop. This is called Turing recognizable, which is at the end, what you are saying is correct, which is that it recognizes it, but it's not part of that language. So if we enter this string to a Turing decidable, it will reject it. But if we classify it as Turing recognizable, it will go on infinite loop. We'll talk about the halting problem. Next handout, we'll talk about the halting problem, and this would be very clear for you, Colin.
Perfect. Thank you, Professor.
Yeah, is it clear now for the time being?
Yeah, that makes perfect sense. Thank you.
Okay, you are welcome. So the coming handout, let me see the class note, the next class note. Oh, okay. Yes, it's after handout 9. Okay. So do you see handout 9? Yes or no, guys? Okay, thank you. Thank you. Thank you. Okay, so here we'll talk about a new topic. It's not new, it's like a continuity. So handout 7, 8, and 9, they are connected and talking about the same thing, which is a Turing machine. But here we'll talk about what a type, we call it universal Turing machine, the halting problem, and we will reach to point that we'll talk about undecidable languages. So with this, it will be the concept will be more clear for all of you guys. And here we'll have a new term, we call it Turing completeness and universal computation. Turing completeness and universal computation. So we talk about Church-Turing thesis, about Turing recognizable and Turing decidable and computable function and countable function. So if we recall that thesis, essentially state that if a problem P can be solved using, here also solve this double, using an algorithm A, it can be solved by some Turing machine. So algorithm A solves P, Turing machine M solve problem P. So If there is an algorithm A that solves certain problem, then there is a Turing machine that can solve that problem. Because in the algorithm, we can solve it in pen and paper. So we need a computation machine or an automaton to solve that. So we should have a Turing machine that can solve that problem P using that algorithm. So assume that we have a computational system, we call it S. If I could somehow prove it can simulate any Turing machine, if I could somehow prove that Turing machine M, some instance of system S, then by Church-Turing thesis, I can prove that algorithm A, it's an instance of the system A, or if it's a set of algorithm or steps, so it's some instances of system S. The implication is that the computational system S can be used to solve any problem that is algorithmically solvable. If I have any mathematical algorithm or any algorithm that can solve any problem in pen and paper, then the system S can solve that problem by instructing the computing machine to do these algorithm steps to be performed. Then we will arrive at the solution that we are looking for. What do you mean by Turing completeness? A computational system S is called Turing complete if it can be used to simulate any Turing machine M. That is, S is a Turing complete if it can be used to simulate the functionality of any Turing machine. So S is Turing complete if S can be used and I have the required thing and the required computational devices or controls to do the functionality of the Turing machine that we are looking for to solve that problem. This notation of simulation will become important when we talk about universal Turing machine. But for now, it is also useful to talk about real-world programming languages. Turing completeness is useful in the context of real-world computational system, programming languages, for example. For example, if you design a new programming languages, you decide to have a new programming languages, not C++, not Java, not Python, whatever. So if you design a programming language and you can prove it was Turing complete, if you design a programming language and you proved that it is a Turing complete, then you will have proved via the CT thesis, Church-Turing thesis, that your programming language can compute anything any other Turing complete language can. So again, if you design a programming language and you can prove it is Turing complete by CT thesis, you prove that your programming language can compute anything other than complete language can. What do you need for a language to be a Turing complete? Not that much. Like C, you need the ability to read and write from a memory. If statement, go to statement. This is what you need. This is what you need. Turing completeness of C. Consider the following description of a Turing machine. A two-state busy beaver. What is the busy beaver? You can go to the wiki and read it. Just click on the slides, you'll have. So, like in C, stdio.h, integer main, integer tape 10, location. So here we initially state the tape that all tape or all cells are zeros. Integer star head, which is a pointer to the tape 5, which is the head in the middle. We make the head in the middle of the 10 memory locations for the tape. State A, if not, pointing to head. If read 0, then head equal 1, write 1, head plus plus, move to the right, go to state B, here to state B. Else, if head equal 1, head minus minus, move to the left, go to state B. What will happen in the state B? So if it's 0, go to the right, replace it with 1 and move to the right. If it's 1, move to the left and go to state B. In state B, if it's read a 0 on the, if we go right, then we'll move it to 1, head minus minus, move it to the left, then go to state A. Else head equal 1, go to halt and accept it, halt, return 1. So as we said, for Turing completeness with C++ or with C programming languages that we can read and write to the memory, we have an if statement and we have a go to statement. Then here we represent it. This is just for clarification. I will not ask you to write any code, guys, in the exam, in the final exam. Just for you to understand. What is the concept of universal computation? What is the concept of universal computation? A computational system that is Turing complete is capable of universal computation and is in most cases what we mean today by a term computer. So universal computation, what we have today, like a computer. This is an important distinction because there is a computational system like a clock, calculator that cannot do anything, any problem or solve any problem, but they are capable of some form of computation, but are not Turing complete. Something to consider next time you will see a commercial where they are claiming your toothbrush as on-board computer. Okay, so I'll stop here today. If you have a question, ask. I don't wanna, but I took those 3 handouts one after each other. Next, we'll see class note 11 till the point of undecidability. Then we'll study the undecidability and continue. And we'll see with the halting problem, the Turing unrecognizable problem, all of these things with what we call it class note 11. So if you have a question, feel free to ask. If you don't have, feel free to leave. And see you tomorrow. Thank you, Andrew. Thank you, Andrew. Have a good one, you too.
Thank you, Professor.
Thank you, Megan.
Hi, sorry, Professor, do you mind if I quickly follow up with you on that question I asked earlier?
Yeah.
Awesome, thank you so much. Yeah, so what provided some clarity for me is when you clarified and sort of reiterated that one was a subset of the other. And so in that case, you know,
yeah,
sort of being a little bit more plain language.
Okay, just a second. Let me share.
No worries.
So to be in the same page. You see here, Turing decidable is a subset of Turing recognizable.
Okay, awesome. So I could take the same language, let's say L1, take it from a machine M0, and that M0 could see it as a recognizable language, and then I could take that same language L1, move it over to M1, which is now another Turing machine, and that machine could recognize that language as decidable, and so it would technically be a recognizable, decidable language.
Yes. So any decidable language is a recognizable language, or any decidable Turing machine is a recognizable Turing machine, but not any Turing recognizable is Turing decidable. This is the difference. Here I have two cases, accept or reject. As you see here, we said we have three cases, accept, reject, loop. If it's accept and reject, it will be decidable and recognizable at the same time. But if it's loop forever for certain input, then it will be recognizable because it accepts my string or my language. And it starts running, but it's never halt.
Perfect.
So it's clear now.
No, that's awesome. Thank you so much, Professor. I really appreciate it. Have a great day.
You too. Alex, you have any question? Brandon, do you have any question? Hello? Okay, guys, I will end the meeting here and stop recording. See you tomorrow.